Good afternoon. My name is Vanessa Blanc. I am microbiologist and responsible of the Translational Science and Development area at Dental Research Center. Today, the Aula Dental is focused on the mechanism of action of the two most important antiseptics in oral care. Let's go ahead. Well, I want to begin this slide, which shows the phylogenetic tree of bacteria kingdom. In the figure, I have marked the location of the main bacterial orders and families that are found in the mouth. And in this list, their most well-known representatives. Notice the great diversity that the oral species are evolutionarily very far from one another. The bacterial variability in the mouth is very high. This great microbial variety of the oral bacteria explains the great metabolic diversity that we find in the biofilms that grow on teeth. So these three-dimensional structures made up of groups of bacteria in layers and layers of microorganisms are protected by an extracellular matrix. Here in this picture you can see in yellow that they themselves produce. This matrix is key to survival at both subgingival and supragingival levels. The differential environment that exists between the superficial and deep areas in the biofilms determines the enormous variety of species that can be found. You can see the differences in the oxygen concentration, the pH, or the nutrient and metabolites are different in the deepest areas of the biofilm and in the surface. And naturally, they create these complex structures, like you can see here. This is a biofilm on titanium implants. One of the most important characteristics of bacterial biofilms, including oral biofilms, is the high resistance to elimination. We eat, talk, drink, and biofilms stay attached. This is thanks to their adhesins and the extracellular matrix by which they are covered. Here you can see the extracellular matrix, and also here. These glucans are always covering the biofilm. So this matrix prevents the proper functioning of cells and molecules to the immune system and the penetration of antibiotics and antiseptics. These molecules are trapped in the matrix and in many cases are inactivated. One example of this, which I just mentioned, is this study evaluating the concentration needed of three different antibiotics, tetracycline, amoxicillin, and clindamycin, to inhibit the growth of all these bacterial species grown in biofilm form or in suspension, that's in liquid culture. And therefore, if we take, for example, Prevotella intermedia, we can see that we need 64 times more tetracycline to kill this bacteria when it grows as a biofilm compared to planktonic culture. Now let's focus on the antiseptics. These are their definitions and clinical effects. Name them. Antimicrobial agents are chemicals that have a bacteriostatic or bactericidal effect in vitro that alone cannot be extrapolated to the efficacy in vivo. The plaque-reducing or inhibitory agents can have a direct effect on the plaque formation, going one step further than the in vitro experiments. The real anti-plaque agents are chemicals that have an effect on plaque sufficient to have a benefit against gingivitis or caries. The anti-gingivitis agents are chemicals that reduce the gingival inflammation and the bleeding also, without necessarily influencing bacterial plaque. And the anti-periodontitis agents can fight against the subgingival biofilm composed of real pathogenic microorganisms. So let's focus on the gold standard molecule for the periodontal diseases treatment. Chlorhexidine is a cationic bisguanidine that was synthesized in 1954 to provide a very broad antimicrobial spectrum molecule, and it was introduced for human use in 1957 in the Great Britain as an antiseptic cream for skin wounds. In the United States, appeared as a 4% solution used as antimicrobial skin cleanser, and in the 70s captured the interest of the dental world when it was introduced as 0.2% mouth rinse in an experimental gingivitis study. In Europe, it was accepted sooner than in the USA, where more studies were necessary to reduce the use concentration. So you know that in the United States, the concentration of chlorhexidine is more usually 0.12% than 0.2%. Well, which are their main side effects? We have to name the biofilm staining, the biofilm that grows on the enamel, the dental calculus, bitter taste, and some reports of mucosal irritation and desquamation. Well, let's take a look at its mechanism of action. The chlorhexidine exerts a direct action on bacteria. At high concentrations, it can be bactericidal, and at low concentrations, bacteriostatic. This is because these two positive charges located at the ends of the molecule, and through them it strongly binds to bacterial cell membranes. This is what I'm explaining. This is a bacteria, this is the cell membrane, and this bacterial cell wall is composed by a big layer of lipids built of phospholipids. This is a unity of phospholipids, is the same like this. And these units have a phosphorus atom in which, when combined, forming the head of the phospholipid, has a negative charge, making it so that the entire surface is completely charged negatively. So the positive charges of the chlorhexidine can interact with the negatively charged phosphates of the lipid bilayer. This is an example. The chlorhexidine molecules group together in the lipidic bilayers, displacing the phospholipids and generating pores in the membrane. So what is the consequence of this? An osmotic imbalance in the cells, an increase in the permeability of the wall, the exit of the cytoplasmatic content to the extracellular space, and at the end, the death of the cell. And I'm going to show you one experiment about that. This is Pseudomonas stutzeri that was treated with 0.1% of chlorhexidine, and after 5 minutes of treatment, we can observe the rupture of the external membrane and the release of the intermembrane content. This is a gram-negative microorganism. And at 15 minutes, we can observe the rupture of internal membrane and release of cytoplasmatic content. Here you can see. After 30 minutes, you can see the cell lysis. Now this cell is dying. And after 60 minutes, 1 hour, we just can observe a bacterial ghost. This is the typical structure that we say bacterial ghost, completely die. Well, this direct action of the chlorhexidine of bacteria can have an immediate effect, or due to its ability to strong adhere to many sites in the mouth, the chlorhexidine can interact with carboxyl groups of proteins from the acquired follicle and enamel, or with soft tissues, especially it binds to anionic glycoproteins, phosphoproteins of the oral mucosa in the palate and lips. So the molecules of chlorhexidine are gradually released, especially due to the action of the calcium ions that are secreted by the salivary glands. So the chlorhexidine molecules are released slowly. So this way it can control the bacterial overgrowth for many hours after the use. So in fact, there are some studies that can found low concentration of chlorhexidine in the saliva of some patients, preventing colonization during that time. The indirect mechanism involves preventing the formation of a new acquired pellicle. The chlorhexidine binds to salivary glycoprotein residues, preventing bacteria from recognizing these binding sites, and therefore the biofilm cannot settle. Now, let's take a look at the Cbc molecule. It's a monocationic antiseptic, antimicrobial, anti-plague, with a substantivity of between 3 to 5 hours that absorbs rapidly to the mucosa and on enamel, but it's also eliminated rapidly. The Cbc is effective against gram-positive, gram-negative bacteria, viruses, some viruses, and fungi, with a similar spectrum to chlorhexidine in vitro experiments, and is more effective than gram-positives. It has been recognized as the FDA Plague Subcommittee as safe and effective for the treatment of plague-induced gingivitis when formulated in mob rinses in 0.5% concentrations ranging 0.1%. And here you can see another uses of this molecule as antimicrobial treatment in food processing industries, like with salmonella, against salmonella, Campylobacter or Staphylococcus, and is used in cleaning and disinfection in pharmacology. So let's see its mechanism of action. So the polar, here is the polar and non-polar regions of the molecule cause CPC to behave as a positively charged cationic surfactant. And this is really important because the CPC molecules can bind to the negatively here charged surface of the bacterial cell membrane, similar to the chlorhexidine process. So the non-polar region, the tail of the CPC, so CPC has a long tail, and this is the non-polar region of the molecule that can penetrate the bacterial cell membrane and the vial, altering it and generating an imbalance in the osmotic regulation, causing again the loss of cytoplasmatic material and ultimately cell death. In parallel, CPC makes the proteins of the acquired pellicle more hydrophobic, which means that the bacteria do not stick so much to the animal and that the biofilm form is also weaker. So we can eliminate more easily the biofilm if we use CPC. Well, a very important characteristic that CPC seems to have is its ability to degrade extracellular matrix biofilms. So for this reason, we consider it a key molecule in our formulations, and this is demonstrated through our internal research. Let's see. We grow multi-species oral biofilms. This is a biofilm of 6 multi-species biofilm pathogenic bacteria under in vitro conditions in our lab, and observe them using atomic force microscopy. We see little, you can see also little definition of the biofilm because it's covered in matrix. You can see how the bacterial morphologies are poorly marked. These biofilms were then treated with a 0.07% CPC solution. And after 30 minutes, we observe biofilms with more pronounced, here you can see, peaks and valleys. We can see topographical protrusions and valleys due to the absence of an extracellular matrix compared these images. And after 45 minutes of treatment, we could hardly see biofilm. What we saw was the addition substrate with hydroxyapatite. So the biofilm has disappeared. Well, then we thought, all about the extracellular matrix hyperproducing bacteria. Okay, we see that CPC was really good at eliminating the extracellular matrix. So our challenge was to see if the CPC can degrade the matrix produced by Streptococcus mutans, that you know that it's a hyperproducing matrix bacteria. So we developed biofilms of Streptococcus mutans for 24 hours, and we treated them with 0.07% of CPC. So we observed these biofilms using optical microscopy, and we saw that after 10 and 20 minutes of treatment, CPC had degraded most of the extracellular matrix. Marked in green, the colonies of mutants, and marked in magenta, the extracellular matrix that these bacteria produce. These treatments also caused a biofilm mortality of near 3 orders of magnitude relative to the negative control. And this is important because we demonstrate that the CPC can degrade the extracellular matrix, but this CPC can also kill microorganisms. Well, another technique for evaluating the true efficacy of oral hygiene products for daily use in vitro is seen in this study. We developed subgingival oral biofilms composed of periodontopathogenic bacteria, and then we treated with 3 different mouth rinses. 1 mouth rinse with CPC, and another 2 mouth rinses with triclosan. And then we stain the biofilms, marked in green the alive microorganisms, and marked in red the dead ones. The differences are high. These differences may be difficult to observe in vivo in the clinical treatments, but in vitro, the analyses are more precise, and these differences show more. By replicating this experiment I have explained, we can know the antimicrobial efficacy of a series of mouth rinses indicated for daily oral hygiene. This graph shows the active ingredients of the mouth rinses selected. This is a product with CPC 0.07%, stannous fluoride, CPC 0.05%, essential oils, and again 2 formulations of triclosan. And you can see that the survival rate of the biofilms treated are completely different. Sometimes in vivo it's difficult to see these differences, but in vitro they are clearly different. Well, clinical studies, rather their review, support the effectiveness of the CPC for the prevention of plaque and gingival inflammation. This is really important because clinically you can obtain an advantage of using these products. And the CPC products designed by the Untitled company have studies that back their efficacy as a plaque inhibiting agent and for preventing inflammation at the concentration of 0.07%. Well, if both molecules, chlorhexidine plus CPC, are combined, the concentration of chlorhexidine can be reduced, yielding the same or superior efficacy. So these images show multi-species oral biofilms treated with different chlorhexidine formulations. And we calculate the percentage of mortality caused by treatments with chlorhexidine plus CPC, chlorhexidine 0.2%, and chlorhexidine 0.2% plus anti-discoloration system. It's an anti-staining system. 3 different formulations on the oral market. So via confocal microscopy, we clearly observe differences in efficacy within the products. This picture represents that. What happened? The problem with the anti-staining system is that it works because these chlorhexidines do not stain, but they greatly reduce the bioavailability of the chlorhexidine, and therefore their efficacy also diminishes. compare the percentage of mortality caused by these two formulations in the in vitro oral biofilms. So these experiments are key to showing the combinative effects of using mouth rinses with 0.12% chlorhexidine with CPC. We think that CPC allows chlorhexidine to reach the deepest parts of the biofilm, and because it degrades the extracellular matrix. And these techniques allows us also to evaluate how formulations with the same concentration of chlorhexidine, here you can see 3 different formulations, all of them with the same concentration of CPC, 0.12%, do not work equally. Remember, in green, alive microorganisms, in red, the dead ones. Aiding CPC greatly increases the bacterial mortality. Well, for us, it's very important for ammonia rinse to be able to penetrate the biofilm, to keep bacteria in the deepest areas of the biofilm. So we conducted this experiment to try to demonstrate this. So this biofilm, this is the surface of the biofilm, this is the surface of the biofilm, this is the surface of the biofilm, and this is the bottom of the biofilm. Here you can see the surface. This is hydroxyapatita, so this is the deepest area of the biofilm, and this is also the deepest area of the biofilm. So we observe through confocal microscopy these biofilms, and then we treat it with period intensive care. This is a time-lapse experiment. It's 20 minutes of treatment concentrated into 5 seconds, and this happens. As you can see, the mortality is achieved. I'm going to repeat. The mortality is achieved throughout the entire depth of the biofilm. So for us, it's extremely important to kill not just the first microns of the biofilms, but also all the deep of the biofilm. Well, if we compare the antimicrobial efficacy of a series of mouth rinses with chlorhexidine, it's clear that different formulations with the same concentration of chlorhexidine work very differently. Here, I've marked with the same colors the bars of formulations of chlorhexidine that share the same chlorhexidine concentration. And you can see that this is a formulation that works much better than the other concentration of than the other formulation with the same concentration of chlorhexidine. Here you can see marked in purple all the formulations tested of chlorhexidine 0.12%. This chlorhexidine is 0.12%, and the survival rate of the biofilm is less than 5%. And also this is a formulation with chlorhexidine 0.012%. So not all the formulations that share the same concentration of chlorhexidine works equally. Clinically, well, formulations with 0.12% of chlorhexidine plus CPC, this is 2 clinical studies, are as effective as chlorhexidine 0.2% with alcohol. Here you can see the studies. The researchers could not find statistically significant differences in the biofilm reduction. So we have an efficacy equivalent between these 2 formulations. And even if we compare formulations with 0.05% of chlorhexidine plus CPC with formulations of chlorhexidine 0.2% plus alcohol, both formulations showed similar anti-plaque and anti-gingivitis efficacy after 1, 3, and 6 months, but with reduced subjective side effects for the first formulation. So here, again, we demonstrate that both formulations have similar anti-plague and anti-gingivitis efficacy. And this is really important, especially specifically because the side effects. Well, I'm going to finish my presentation by mentioning the recent literature published on the possible activity of CPC against viruses that cause respiratory infections. The first study I want to show you is this one. It was published in 2017, and it shows how CPC rapidly degrades the envelopes of different flu-causing influenza viruses. Its application did not cause the viruses to be resistant to CPC. And also, in the same study, it's shown that 0.1% of CPC could be effective in the prevention and treatment of influenza virus infection in a mouse model. Let's see more in depth this study. Here you can see a table of a range of concentrations of CPC that researchers use it in order to degrade the viruses. The concentrations used range between 5 micrograms per milliliter to 12.5 micrograms per milliliter. This range was very effective against different, here you can see the different strains of influenza studied, even against 2 oseltamivir resistant strains. So all these concentrations could eliminate up to 50% of the viral load. You have to think that in oral care, we can use up to 1,000 micrograms per milliliter of CPC. So these concentrations are really, really low and they are effective. The transmission electron microscopy analysis showed that while the viral envelope of untreated influenza viruses was intact, the exposure of these viruses to CPC led to the disruption of the envelope and gross distortion of viral structure. Here you can see a cavitation, and here again, these viruses were treated with CPC in a concentration of 50 micrograms per milliliter. And you can see even the presence of negative stain in the interior of the virus treated with CPC, but not in the untreated virus, suggested the permeabilization of the viral membrane. So this is really important to observe that the viruses are inactivated because their membranes are degrading by CPC. And to further confirm that CPC disrupts the influenza virus envelope, these same researchers use a ELISA technique to monitor the release of nucleoprotein from viruses in response to increasing concentrations of CPC. So the viruses were treated with these different concentrations of CPC, and then they check the increase of release of this, it's a protein of the nucleus of the virus. So they found that the exposure of virus to increasing concentrations resulted in significantly increased levels of viral nucleoprotein into the media supernatant. So taken together, these results demonstrate that CPC can act against influenza virus by a rapid disruption of the viral envelope. And the authors make this statement. It's likely that CPC would also have substantial activity against other enveloped viruses, such as respiratory syncytial virus, parainfluenza, and coronavirus. So I have placed in this slide 4 different types of virus. They are completely different, but they share one morphology. All of them has an envelope composed of a lipid bilayer of phospholipids. And this is really important because one could hypothesize that if CPC can disrupt the envelope of this influenza virus, could also disrupt the envelope of coronavirus or hepatitis V virus or virus respiratory syncytial. The authors hypothesized that, and in fact, last year, these researchers evaluated the activity of at least 36 inhibitors of coronavirus, and they found that the cetylpyridinium chloride could be a really good inhibitor of especially the MERS coronavirus. So, well, these are really good news, really good news. And the only study that has been conducted using CPC is this study that I'm sharing with you. It was done on human beings to evaluate the efficacy of using an oral formulation in the form of a spray with 0.1% of CPC on an infection by viruses that cause respiratory infections. So the incidence and severity of infections processes in 94 volunteers are evaluated in comparison to placebo. Some volunteers used placebo and some volunteers used the active spray, and the results are significantly different for the two groups for the variables studied. So therefore, the oral research scientists are facing a great challenge. The existing research is very incipient, but it seems to indicate that the use of oral mouthwashes with highly bioavailable CPC could have preventing effects on the contagion and spread of viruses among the population. And of course, more studies are needed to solidify this hypothesis. And that is what we are working on. So this is the end of my presentation. Thank you very much for being there. If you have some questions, we have some time to answer some questions. Okay, is there any? Yes, well, some of you are asking if there are any research for chlorhexidine plus CPC in reducing buccal viral charge of this SARS-CoV-2. Yes, we are now running several types of experiments, proof of concept and long use of these moon rinses in COVID-positive patients, and also in clinicians that they are helping that COVID-positive patients in order to avoid the cross-contamination between the patient and the clinicians. We have several clinical studies running, but I have no data. Yes, the second question is the same. What about effectiveness against COVID-19? We don't know. We suppose that the CPC is a surfactant, so it should be considered the soap, the same soap that we use to clean our hands. It's the same concept in the oral cavity. So we think it could be really useful based on the studies that I have now showed you. Yes, we recommend, we are doing all our dental colleagues and periodontologists to recommend your patients to do a mouthwash of 1 minute, not 30 seconds, 1 minute with chlorhexidine plus CPC or CPC of high concentration. I mean 0.07%. Is the antimicrobial effect of chlorhexidine potentially by the detergent? Yes, I'm sure that the antimicrobial effect of chlorhexidine is potentiated by the detergent action of CPC, especially in the extracellular matrix. Is the action of CPC of antimicrobial? It depends. The CPC has an antimicrobial efficacy alone and can be used in order to control the overgrowth of oral biofilms, to inhibit the overgrowth plate, to control the inflammation in the gingivitis cases, but not for periodontitis. If you have to control a periodontitis, you have to use the combined elements, chlorhexidine plus CPC. Is peroxide dihydrogen better with reducing coronavirus? I don't know. In fact, we are discussing that with our colleagues because there are no evidences. I know that World Health Organization and many dentistry associations have recommended to do a mouthwash with peroxide hydrogen, but in fact is an old recommendation, but we do not have a clear evidence about that. You have to think that peroxide is really oxidizing element, and I recommend if you want to use just one use, because the side effects can be really a big concern. Okay, CPC will be a good alternative to, could be CPC 0.07% could be a really alternative for preventive effects. Yes, but we are searching that. We are on that nowadays. I use, and my family we use a lot. So does CPC has any antiviral? We don't know if chlorhexidine has any antiviral efficacy, but we are testing in one arm of our studies. We are going to evaluate if the CPC, if the chlorhexidine has I suppose that can do some antiviral activity, but we suspect that no so effective than the Cbc molecule. But we don't know. In these situations, can small children use periodite? If so, what age? Wow. With children, we do not recommend chlorhexidine, even nor with prevention, nor if you don't have any problem. Don't use chlorhexidine for children if you do not have a recommendation of your dentist. Don't do it. If you want to prevent a cross-contamination with your family, if you have some COVID positive patients, use CPC at the concentration of 0.05%. You have to think that children younger than 6 years old, we do not recommend to use antiseptics, never. About the stainings, well, of course, it has been demonstrated. I told you that the chlorhexidine and also a bit less the CPC can stain, but you have to think in health, not in beauty. If you have a periodontitis, or if you want nowadays trying to prevent the infection of coronavirus or another respiratory viruses, you have to protect first. This staining can really be eliminated using a professional cleaning. So don't be worried about that. I'm not worried about that. Okay, so I think we do not have more questions. Can you recommend, just only the last question, can you recommend daily oral care products containing CPC? Yes. Yes, I recommend, especially in nowadays, I recommend for prevention, avoiding contamination of infection diseases like viruses. And I recommend for avoid the overgrowth of dental plaque if you cannot control with your toothbrush. If you have problems, in order to control mechanically the oral biofilms, use CPC. So I think I have no more questions. So you can send all the questions to our email, and we are going to answer you as soon as possible. Thank you very much for being there, and have a nice week. Have a nice evening. Bye.